Okay, good. So you can see my screen as well. Actually, 2 weeks ago we started. We mentioned that we're going to discuss hidden Markov chain and do problem this week, but my notes are not ready yet for those two topics, so we probably have to defer to another 2 weeks. Other than that, just a summary that last week for the for the office hours we covered homework 2 and 3. So far we covered all the homeworks up to homework 4. And then today we can go through week 7 and week 8 materials. And then in addition to that, we can go over homework 5 and homework 6. And then you have all the grading for homework 1 to 5. Again, if you have any questions regarding your grading or regarding your grades or regarding any of the questions, let me know so that we can try to make sure that you understand the problems. And in addition to that, we discussed the project briefly last week as well. And then let me quickly take a look at the schedule. Okay, next weekend, by the end of next week, you need to form a team. So either way, if you plan to, I will have a thread on the Blackboard system so that you guys can try to form teams and put so that we know who is going to work with someone else. And then it can be by one person, can be a 2-person team, and then if you want to, 3-person team would be fine as well. And then if you are just by yourself, you probably work on 2 methodologies. And then if you have a team of 2, you probably want to think about 2 or 3 methodologies. If you have a team of 3, you definitely should consider 3 methodologies for any of the problems that you are trying to solve. And from that, again, I'll just open a thread on Blackboard system so that you guys can form the team by end of next week. And then by the end of week 9, we need to have a project proposal draft. And then if you have any questions regarding the project, also let me know. So you have 2 options. One of them is look at the end of each chapter and then to pick up some problems. And the second option would be just to pick up some real problems that's in your field or in your own interest, or you have some sort of data that it happens that you have those data that you want to do some analysis with. I think it would be a good opportunity to practice on the all the problems all the methodologies that we actually learned in this class. Granted that it's kind of diverse, it has a lot of options. It's still better to choose some and try to use them in your practical problems. Okay, so if you don't have any questions, logistics wise, we can continue with week 7 and week 8 material, and then after that we can cover, hopefully we have time to cover week 5 and week 6 homework. Okay, any questions? No? Okay, so let's just continue for week 7. So week 7, the methodology that we're discussing is modeling using graph theory, and then even though on the surface look like totally different from what we have been discussing, but the reality is all the graph problems, I wouldn't say all of them, but majority of the graph problems can be modeled as a linear programming problem or integer programming problem or nonlinear programming problem. So now you have a sense that what is a linear program, and then we would have some discussion regarding nonlinear program and integer program. So as you would imagine, by now it would be either nonlinear constraints or nonlinear objective functions, and then integer program only takes integer values as a solution, as a decision variable. So that as you would think that the feasible region that we have been discussing is no longer a region, it's lattice of all the discrete points. That's why the solution would no longer be on the vertex, so that it's relatively speaking, it's more difficult to solve. Hold on 1 minute. I have something. I'll get some water. I'll be back in 30 seconds. Okay, let's continue with the discussion about integer program. So we discussed that it would be a lattice of points so that it's harder to solve. And then as the as an extension is something called mixed integer program, and then it's also called MIP. And then given that the reason that it is called mixed is just because it can have some of the decision variables will be integer, some of the decision variables can be just regular fractional values. So you kind of now you can get a sense that why do we need integer programming there. So there's certain cases, for example, we're trying to make tables, we're trying to make chairs, and then those decisions have to be integer. You cannot make 3.5 tables. That's the idea here. So we're going to discuss a little bit more about all those programming math programming methodologies, but in this chapter we're focusing on graph. And then again, majority of the graph problems can be represented as math programming problem. You can see here 8.5 connections to math programming. Okay, 8.1 we're going to discuss the graphs as models and then how to describe graphs, and then also discuss graph models, using graph models to solve problems, and followed by connections to math programming. And then as an introduction, which I already discussed just now, how can we use graph to model math problems? Things like, for example, social network problems, minimum shortest path problems, maximum flow problem, and even the famous TSP problem, traveler salesman problem. For example, UPS guy needs to, in the morning, needs to say that I need to visit this 10 cities, 10 houses, and then what will be my best choice in terms of my how can I decide my route, and then that's a decision as a TSP, traveler salesman problem. TSP problem itself is actually very difficult to solve especially when you have multiple nodes. We'll get to that later on in the class. And then graph as models actually initially started with this famous model called the Seven Bridges of Königsberg. I think it's probably one of the cities in Germany. or somewhere in Europe. And then they say, okay, we have these 7 bridges. How can we model this problem as a math problem or graph problem? So you can see here, there is certain things in this graph that you should know. One thing is called vertex. In this case, is A, B, C, D. Capitalized A, B, C, D are all the vertex. And then all these vertex actually in this graph really representing certain regions on the graph, right? And then correspondingly, and then for example, because that sits smaller case C is connecting region A and C, right? And then that's why corresponding on the graph, we can see that there is a link between A and C, meaning that which is called smaller case C. And then in this case, which meaning that in order to go from region A to C, you have to take this smaller case C route. And then, of course, you can take D route as well, which exists there. So now you can represent that physical map to a graph. And then apparently you could see that I can use C smaller case C on this graph. I can see its direction, or I can say it can only go from A to C, and then correspondingly we could think about C go to A, can use the D link, right? So that there is a direction if you kind of let me see if I can find okay, I can find a pointer, but basically it's just let me see if I can find a hint. Somehow I cannot find the pen. It doesn't work. But anyway, so all I'm saying is it will be directional. A to C would have a arrow there, and C to A has another arrow there, so that it becomes a directed graph. And then one of the famous problem is called graph coloring. Given a geographic map, is it possible to color it with 4 colors so that any 2 regions that share a common border of length greater than 0? So you can define that if it's neighboring, then it's defined as of length greater than 0. I assign a different colors. So that saying that if this one is red, you can now use red on the neighboring state. And let's take a look at the solution. The solution for this problem is apparently for all the states in the United States of America map, you could use 4 different, in this case we use different shape to represent the vertex, and then so essentially it's a color, right? So you can see that none of them have a problem to satisfy the condition of this coloring problem specification. And then how can we describe a graph? And then you have to think about vertex set, or the vertices that we discussed earlier for, or the capitalized A, B, C, D, E would be the vertex set. And then there's an edge set. Edge set is all the links that's connecting all the vertices, so that smaller case C, D in the previous example would be part of the edge set. And then incident, we can say that what is the incident to a specific vertex. So in this case, if we go back here, we will see that edge CD, A, B, and E is incident to vertex A. And then adjacent, right? Adjacent could be adjacent vertex. And then we will define that because A and D has has a connection. That's why A and D are adjacent, and correspondingly A and C are adjacent, and A and B are adjacent. So as you can see that for different terminology we're talking about, sometimes we're talking about links, sometimes we're talking about edges or links. And then degree, how many degrees that's associated with a specific node. For this case, for node C, it has a degree of 3, meaning that number of edges that's incident to this vertex. So as you probably would read the book, you would understand a little deeper on this, but that's a snapshot of what it means. And then see that we kind of went through this already, how to fit in a piecewise linear function to data. And then you say, okay, if we fit a linear function, it probably would be the chart on the left. And then if you fit a piecewise linear function, you could fit the chart in the middle or the chart in the right. And then apparently at this stage, you probably would realize the chart in the middle would be overfitting because it's trying to fit every single point so well, so that there's potential that the model would have not much expandability. So it's overfitting for this particular model. And then if you look at the third possible model, piecewise linear function, let's say that you can try to fit certain pieces as just a linear function. Instead of one linear function, you have three linear functions to fit all the data. This is relatively speaking, piecewise linear function itself sometimes can be a useful methodology. Why is that? Because if you think about it, for this linear function, the first possibility, given that if we want to do a prediction, we say that for x equal to 20, what would be the corresponding value? You would realize that you would extend this line all the way up, so it could be much higher than the third solution would provide, just because of the slope of the line. So remember that I couldn't remember exactly which homework, but we discussed that stamp problem. How do you estimate the price for the stamp? For USPS stamps, right? So for that problem, it does have the potential problem of projection going forward, whether it has issue of overshooting type of problem. I kind of think so. That's why maybe a piecewise linear function might work better in some of those scenarios. Just to give you a sense and flavor here. And then on the so Seka was asking, is piecewise similar to a cubic splines? It's actually not quite, because cubic spline is you can test it, but it would definitely give you a different answer, because piecewise linear just 3 pieces of linear functions, and then cubic splines you have powered by 3, powered by 2. You know how it's set up, so it will result in different solutions. And then following up on this, continue for graph solution based on cost structures. Essentially here we're saying that what if we give some cost on the links, right? 1 to 2 cost 3 minutes, 2 to 3 cost 5 minutes, and 1 to 3 directly cost 6 minutes, for example. In that case, if you want to find the shortest path in terms of traveling time, how can we get 3 quicker? These kind of questions that's part of the solutions that part of the problem, many major problems that graph models can help to solve. And then again, you already see the similarity between the optimization or linear programming and the graph model, as the example that I just mentioned, right? From 1 to 3, what's the shortest path that we can take, and then constraint on 1 to 2 cost this, 2 to 3 cost that, and 1 to 3 cost is z, right? And there's a connection that you can use some sort of constraint to tell the model that x12 is actually exists, and then x23 exists, x13 exists, but not for this graph. It's actually 1 goes everywhere. So, but in certain cases, we can imagine that maybe 1 doesn't go to 4, so x14 doesn't exist, so that you can formulate the problem. And then there is a matching. There is possibility that sometimes you can use a graph to solve matching problem. And then suppose that in this example, we're saying that suppose that R, which is A in this case, he's a all the guys are softball players. And then we say, okay, A can play position 2 and 8. So let's use the for softball players on the left-hand side, and then use a position on the right-hand side. And then you use links to represent whether a specific player can play a certain position. So in that case, A can play 2 and 8, so that A have a link to 8, and A have a link to 8. And then let's look at second player, Bo. Bo can play 1, 5, 7, so B has a connection to 1, has a connection to 5, and has a connection to 7. So that's how you solve. You can represent this problem. And then next question would become, if I say, okay, because we have 11 positions, we have to find a feasible set. Now I'm only talking about feasible, meaning that we have to have someone to play something, right? We cannot say, okay, A can play, because A specific set in this setup, I mean, configuration of the example, A cannot play position 1. We cannot say, okay, let's assign A to position 1. That's not going to be a feasible solution, right? Okay, so in order to find that feasible solution, we can use matching. It's called matching problem. And then matching problem itself is actually a math programming problem. And then if we go a little bit further, we say, okay, what's the best solution for the matching? And then maybe we can say that our plays better on position 2 than position 8. That's possible, right? We can assign that A to 2, the cost being 1, because he's better, and then better on this link, and then A to 8, a cost of 5. For example, if we say that he's much better on position 2 than position 8, and then we can minimize all the cost, all the sum of all the links cost, and then constraint on A can play 2 position, A can play 8 position, B can place 1, 5, 7 position, etc. Mathematically, hopefully I think it's actually in the textbook has a much detailed example, but that's the basic idea there. So let's continue and see if we have something similar. I do believe that we did have something very similar, so that we can at least get a little bit deeper on how this is connecting. And then another example is policing a city. So it's called vertex cover problem. For a vertex cover problem, saying that if we have certain polices and we have a set of police cars, and then we want to make a decision that who is covering which region, and all the region can be defined as certain nodes, as we discussed earlier, right? For the states, we can use nodes, the vertex to describe the state, and then correspondingly we can use some regions, some vertex to represent those cities or regions, and then question is who should be responsible for which city if you have a set of police, and then that's called a vertex covering problem, and also correspondingly in the warehousing problem, like some questions that's facing Amazon, which warehouse should be servicing what region. Of course, it depends on the availability of the products, but let's assume that all the products are stored in all the major warehouses. And then if you're ordering something from New York City, do I use the warehouse in Philadelphia, assuming that there's no other warehouses nearby? Should I use Philadelphia warehouse or should I use Boston warehouse? That would be those type of questions I can answer. And then actually for this vertex cover, I actually do want to go a little bit deeper. Let me find the problem so that you can get a better sense on what it is. So let's see. So here is a link from Wikipedia. Apparently, there are some other better notes from some of the textbooks or some of the lectures, so that you can review as well. But formally, let's say a vector cover problem is an undirected graph. Okay, undirected. When you talk about graph, you always want to take a look. Is undirected or is directed, and then we are trying to find a subset V such that so here it essentially says that it is a set of vertices where every edge has at least one endpoint in the vertex cover. So that, say here, for this solution, right, for this problem, you see that every edge has one vertex that's incident to the red edge, to the red node. So you want to find the minimal set find the minimal vertex set. That's the idea. Of course, that's a vertex cover, and the next question would be, what's the minimum vertex cover? Is the vertex cover of smallest possible size? So, for example, for this example, for the one on the right, you can see that on the top you can choose 4 of them, and then on the bottom you only need to choose 3 of them, so that it covers everything as well. So, and then the one at the bottom would be called a minimum vertex cover. And then let's see if it's and then here is a formulation. Even though it looks complicated, but if it's as simple as if you only have 5 nodes, you would understand that right away. But if you quickly take a look at the formulation, it's really not too bad. So here it says, let's assume that x and u and v is connected with each other. So let's look at the first constraint. That says xu plus xv larger than or equal to 1. So that at least, so that says larger than or equal to 1, meaning that at least either xu equal to 1 or xv is equal to 1. Given that the second Okay, sorry. So here, let's look at the second constraint first. The second constraint actually says every vertex is either in the vertex cover or not, and then say that xv is either 0 or 1, and xv meaning this vertex v is in the in a vertex cover, right? So let's call that the red dots as vertex cover, so that if u and v happen to be connected, then that xu and xv should be plus xu plus xv should be true, meaning both of them are 1, right? So and then if we use xu plus xv larger than or equal to 1, then we see that u and v, the edge between u and v is covered either by u or by v. That's the first set of constraints. And then the objective function is trying to minimize the total cost, and then x sum of all the xv, because if minimum vertex cover problem, that you would have this constraint, this objective function. And then if we have certain costs associated with the xv being the vertex cover, then we can embed the cv there. But if we don't have a cost associated, then it's really just minimize sum of xv. So that would be the vertex cover problem. And then apparently it's so abstract in this stage, you probably wouldn't be able to see too much potential application yet, even though I already give you a sense. You could have the Amazon example that you would realize right away how this may be potentially being used. Okay, so let's continue with that, and then next one is shortest path problem, and then the famous Dijkstra algorithm is on page 324. Go through that algorithm, and then we would have homework problems on this one, and then algorithm for maximum flow. How can we get maximum flow through the network? And then textbook further discussed how to use bipartite matching problem. Bipartite matching problem is saying that you have, as we discussed, those players versus the positions is x1, x2, x3, and x4, and then y2, y3, all the way to y6 would be the part of the matching problem. And then if we add some supplementary nodes, one is S, the other one is T, and then we have cost of being 1, we can transform the matching problem to a maximum flow problem. And then apparently, once you read the text, relatively speaking, it wouldn't be really difficult. Conceptually, the formulation wouldn't be very difficult. It's just that how you can actually model your problem as something similar. For example, in this case, matching problem even can be translated to a maximum flow problem. And then again, traveling salesman problem, tour, cost, and then in this case, the optimal solution is ADCBEA. And then actually I want to go through the formulation, hopefully very quick, on the traveler salesman problem formulation, because we are here. I just want to go through the formulation. This formulation is really not as straightforward as it looks. And then question is, so as I just discussed earlier, TSP is trying to visit all the vertices and then come back to the depot. And then it's going to be just a 2, right? And then if suppose that it can be formulated as an integer linear program. Let's label the cities with numbers 0 to n and define xij equal to 1 if the path goes from city I to city j. Otherwise, it's 0. So we're saying that for this case, it would be from this I to this j, it becomes 1. And from this I to this j, becomes to 1. That's the idea. And then let's continue and see here. So let ui being a dummy variable and finally take cij to be the distance between city I and city j. And then the TSP can be written as the following integer linear program. What is it? It says, let's look at this constraint first. Sum of xij equal to 1 from 0 to I is now j. So this is saying that from 0 to, you have to go out. 0 is really the depot. From 0, you have to go to somewhere. That is to say that you have to go to some node, right? That is this constraint. I'm not sure if you can see my pointer here, but hopefully you can, which is the third one, one, two, three, the third constraint. Yeah. And then the fourth constraint, sum of j equal to 0 to j doesn't equal to I to all the n xij equal to 1, it says eventually you have to come back to the depot. J is 0. So going back, it has to go back there. So xij has to be 1. That's that. And then for anything else, xij is larger than equal to 0 or less than equal to 1. And then uij belong to this set of z. Z is defined as what is UI? UI be the dummy variable, and finally, I didn't mention here, but I couldn't remember on top of my head either. UI is, yeah, I need to think about it. Yeah, let me do a little bit more research. Hopefully next time I'll be able to come back again. But I actually what I really want to touch upon is the last constraint is something called trying to avoid sub2. And then our uij is some sort of dummy variable. Uij can be anything, and it's associated with each single node. And then that's why uij would be used as the as the last constraint. And then this constraint is used to avoid sub2. Sub2 is defined as it is possible that you visit all of them once and then you visit all of them the rest of the graph one time as well, but you actually have 2 tools instead of 1, or 2 or more tools instead of 1. So in other words, without this last constraint, you would end up having multiple tools and visit all the nodes once, still have a solution. So the last constraint is called avoiding subtool. So trying to you should read a little bit more here and understand why this one is defined as this particular form of the equation is actually not as difficult, but definitely worthwhile to take a look. I want to give you a sense there. So we should actually try to prove here why it is in that particular form. And then just want to mention it is NP hard problem, and then it's much difficult to solve than you think once the node is becoming the number of nodes becoming really big. And then here I actually give you some examples of how it is solved, get a sense on how it actually solved. That's from Wiki. That's actually I want to discuss here. That's pretty much everything. And then again, we actually already discussed vertex cover problem, and then it is mass programming. It is linear programming in this case. No, it's actually integer programming because xi has to be either 0 or 1. So it is an integer programming problem, sometimes also called a binary programming problem, because xi can only take binary values. And then maximum flow. This constraint, you should read the textbook, but I just want to point out that this is really called conservation of flow, meaning that anything goes into J has to come out from J. That's why sum of xij for all I going into J is on the left-hand side, and then on the right-hand side, anything goes out from J has to be sum after the summation has to be equal to the left-hand side. That's a conservation of the flow, and then this constraint actually explains that. And then J belongs to all the vertex of the graph. J belongs to VG. G is the graph. V is all the vertex set, and then J is a vertex essentially in this case, right? And then S and T, including S minus S and T, meaning not the starting point and the destination point. S usually is used for the starting point, and T usually used as a destination. And then there's apparently the second constraint is the capacitive constraint. Xij has to be less than or equal to Uij on the edge between I and j. And then Xij has to be larger than or equal to 0, non-negativity constraint for the last one. And then the objective function is trying to maximize all the flow that is from S to any of the points, starting from S to any of the points. Sound that is the maximum flow problem. And then this is a homework. So again, you only need to pick 3 of them, and then I believe one of them probably is a matching problem, one of them is a shortest path problem, and at least one of them is probably a maximum flow problem. So it's rather interesting to explore some of them for sure. So let's continue with week 8. Okay, week 8 is decision with modeling with decision theory, and then this is somewhat taken a little bit to divert. I would say that it's a little bit divert from what we just discussed. It's no longer graph, no longer linear programming, and then it's something called decision theory. And decision theory is just trying to see what's the expected value based on the probability, and then discuss the decision trees and sequential decisions and conditional probabilities, decision under alternative criteria. Okay, Neil was asking for the homework 2 on the 330, whether it's on page 331 that we just was looking. I think most probably yes, which I don't have a textbook handy, but if it happens that if you see it on the 331, just use the example in the problem on page 331. It's not, I can confirm that as well, but for now, let's assume it's there. Okay, and continue with this decision on the alternative criteria. So once you learn probability, you probably already realize the importance of expected value. And then here we go a little bit further to see how can we make a decision based on the alternative options or alternative criteria. And then for any of the problem, it can be deterministic, can be risk. If it's associated with some sort of chance or risk, then it's stochastic. And then a lot of the decision problems are stochastic problems. And then this is not new. And for chance or risk, it's stochastic problem. And then you can use probability to get the expected value, to get the weighted average, can do the sensitivity analysis. Here we got how to define the expected value based on the weight and the corresponding payoff. Payoff is a weight, and probability is the weight, and weight is payoff is really the W here that is used, and then we can get the expected value of the gain. And then for decision tree, that is it has two type of node. One type of node is called decision node, and one type of node is called probability node. And then in this case, the circle node is the probability node. In this case, we say, okay, if we have a new construction, and then if it's successful, we probably have a certain payoff, and then if it's not successful, we have certain cost or certain payoff as well, which conceptually would be less than the first option. And then for the second one, I'm just trying to get my pointer. Yeah, and then for the second node here, it's saying that if earlier we made a decision on remodel, and then if the remodel being successful, and it has a certain probability associated with it, and then what's the corresponding payoff here? And then what if it's unsuccessful? What would be the corresponding payoff there? And then this tree could help you to make a decision on at this decision node. Should I take the new construction or should I take the remodel route if I have a house that I need to make a decision on? Should I tear it down and make a new construction, or should I just do some remodeling there? And then also one type of example would be sequential decisions and conditional probabilities. And then in this example, it use some sort of spinning, and then make a decision on. And then usually, in order to calculate the expected value for the first decision, you should always go from the end of the decision tree, going backwards, essentially. So let's take a look at the first one. For example, if you spin, you take spin $10, take with a probability of 0.25, your expected value for this branch would be 2.5, plus for the second one, you take $6 and then probability of this happening 0.25 times 6, that's 1.5. So we have already have 2.5 plus 1.5, right? That's 4 already. And then for the third one would be 4 times 0.25, and then you get $1. That would becomes 5. And then for the third possibility, you spin $0 probability 0.25, so that you get $0. So for this particular node, the value of this node is $5. So you keep going back, you would have all different options. And then again, we discussed the square represent a decision node, and the circle represents probability nodes. So keep going back. At the end, you would find in certain spin what's the expected value of the certain spin. That's all possibilities. And then again, if you think about different branches, which one has the highest expected value, maybe in that way you would start thinking about decision making. We would go a little bit further detail in later on in this lecture, I think, very soon. Okay, it doesn't. But let's take a look at the new construction versus remodel example, which is easier to explain in this case. And then there's some investment strategies, which decision should we make, what type of decision we should make. Apparently, many of the problem is not as simple as this particular example, right? So essentially here it says, if we have a certain payoff here, we have certain payoff here so that we can get an expected value of new construction. And then with this, with this payoff and this payoff, you can get the expected value for remodeling. And then ideally, if we have a probability associated with it, with new construction or remodeling, we would have an expected value of this decision. So in other words, even if we don't have an expected value, without this probability, if we want to choose between new construction and remodel, once we know expected value of new construction versus expected value of the remodel, we would be able to make a decision on which one we want to take. So that's the idea. Apparently, this is a very simplified, very fundamental and simple decision tree. A decision tree can be really complex so that you can make a decision at certain points, and the decisions can be sequential decisions, which comes to the next slice here has sequential decisions and conditional probabilities. That's the idea of decision using alternative criteria and how we can apply decision tree in real examples. And then in this, these are the homework for this week, all focused on the decision tree modeling. Definitely work on 3 of them. You'll really get a good sense on what is decision tree after the homework. Okay, so that's pretty much everything for in terms of a lecture that we're going through. And then we only have 2 minutes, but let's quickly go through the homework. Ideally, it would be nice that if you actually already reviewed what you have done and what's in the solution, that would be more beneficial to you in terms of from the learning perspective. Oops, I was trying to close the right hand corner, but closed everything. Hold on. So for homework 5, first of all, first question is regarding that Markov chain or probability of transition from one state to the other. I'm sure you, at this point, you probably have a fairly good understanding of it already. And then want to ask you what's the long-term probability of being a certain state. So in this case, saying that student probably have 80, around 83%. I can remember it's 91% would be on the this dining hall, and 9% would be in a different dining hall. Apparently, this is something that can make it. That's something that school can utilize this information, make a decision on which dining hall should have more staffing, things like that in that nature, right? Okay, and then the second problem is reliability. It's really coming from more like strict application of the definition. And then probability of the whole system liability is being that liability PA times CD plus radio minus CD times radio times S1 plus S2 minus S1 times S2, because this is parallel, and then those three subcomponents are sequential. And then, of course, there's some assumptions saying that they cannot say CD and speaker 1 or speaker 2, one of them has to function, etc. It's really, I think, straightforward, this problem. And then next question is a linear regression problem. Okay, and then now we know what is a linear regression. We can calculate SSE, sum square of error, sum square of regression, and sum square of total sum squares, which is SST. And then you can calculate using SSR divided by SST to get your R square. By the way, some of them, apparently you have to know that how to use it, how to get the equation. Meanwhile, hopefully you know a little bit more about the theory, because if you are on the job market, people would ask you what is R square. You say R square is trying to measure how much variance is measured by the model, how much variance that can be explained using the model, how much variance of the data can be explained by a specific model. That is R square. And then how to calculate R square. R square is SSE divided by SST. And then what is SSE? How do you define SSE? Something like yi minus y hat sum squared, right? Things like this, you got to have, you probably won't need to be, know this on top of your head, but if you are going through some certain interview process, you have to review this, at least remember this, otherwise people would start questioning, looks like you know linear regression, but if you are really trying to ask you some questions, looks like you don't know. So just some tips that you probably want to think about. And then that's it. And then continue with this at how SSE is calculated, how SST is calculated. It's already actually based on the math equation based on these calculations. And then I thought we should provide a residual plot. Here, the solution, I didn't give you a residual plot. Oh, it's probably this part didn't print out. But I'll check that and try, hopefully I can fix it. And then next point is trying for table 2.7 predict weight as a function of height. And then that's a function. Summary statistics with those. And then the residual weight versus height residuals. And then the next question says a function of the cube of the height. And then Oh, yeah, actually, that's a residual plot. Yeah, apologize. It's really that. And then for this problem, we can find the corresponding residual plot, and then you can comment what's the difference between those two, whether it's better or which one is better. It's really not, I don't really see which one is better. And of course, solution actually, one of the students here, oh, by the way, all the solutions are coming from one of the earlier student, two of the previous students in previous semesters. And then in our class in this semester, I definitely see some comparable quality in terms of the quality of the homework solutions. I saw several comparable solutions with this. So if you look at the way that you did it and then look at the quality of the solutions, you would see where I would appreciate if you could further improve. And then some of you are still using Excel to solve some of these problems. I don't have any problems with that, but ideally, I still hope that you can switch to R. Sooner or later, you have to do that, especially after graduation of this program. If you still stick to your Excel, it definitely doesn't make sense to me, and it's not marketable on the market either. Being an analytics guy, and I'm not saying that Excel is not good, but in terms of analytics, apparently it has limited capability in terms of all kinds of analytics that it can perform. But on the other end, R is way better and has much more capability. So again, I encourage all of you try to start using it and also trying to use the homework solutions as some sort of give you some sense that what type of quality that would really um, can get a perfect score, or even better than perfect score. Okay, and then this is that he tried something else. It said that what if I use second order of the height to do a prediction, and then his conclusion is looks a little bit more random in terms of residual compared to the other two models, and then he said it looks better, which I agree. And then he summarized those three models, look at the difference between those three. That's also something you could do because at the end, it's more about the way that you think, the way you approach different problem. It's not that you get the right solution. It's no longer in real world, in practice, in your work, or in all these things. You have to start thinking the way how to think, right? I guess that's the ultimate goal for everybody for all the learning process. Okay, that's the solution for homework 5. And then let's take a look at homework 6. Homework 6 is linear programming, and then apparently, see, the way that I chose all those homework problems, I was trying to use to touch upon all the major concepts that we learned in the specific chapter. That's why if you choose 3, even if you choose 3, that's fine. It would be ideal you take a look at all of them, even though if you know how to do it, that's you can just skip it. I would think that you say, okay, this one, no. But the majority of the time, actually, you probably choose because I think I can get this done, then I just only finish that one instead of the ones that you don't know. I mean, I would think that if it's more challenging to you, it's probably better for you to learn more from the one that you actually don't know. Just a side comment here. But for this number 1, it's straightforward. It's a minimization problem, and then minimize all the cost. Minimize the cost with corresponding constraint of the requirements that you need for in terms of the in terms of per week and per week, so that you have to meet all three requirements in terms of protein, carbohydrates, and roughage there. So that's the constraints with non-negativity constraint as well. Some of you just want to mention that some of you actually missed this last one. In this case, apparently it is important here, right? And then go to next question, that is a linear programming problem, and then you just need to plot each individual constraint. And then in this case, the red line represents the objective function, and then the feasible region is shaded. And then we're trying to minimize so that we're trying to minimize in this example, or maximize in this example, so that apparently the solution would be 0 and 8. And then I think some of you probably made some mistakes. It's I believe majority of you actually got the feasible region correct, except that the objective function is probably not with the right slope. That's that. Next question says, okay, how can we solve the same problem? Use algebraic analysis. In the book, the algebraic analysis specifically meaning the method that you test on all the possible vertices and then get the final solution. Again, pick the one that actually makes sense. And then here, for all the extreme points, and then you can get the corresponding all the extreme points with the slacks in this example, and then try to get the objective function. You can pick the maximum value in this case. And if we continue, the next one is how to solve it actually using simplex. Again, many of you actually get a chance to practice this in manually, which I really appreciate that. And then if you continue, basic idea for simplex, if you already did the homework, you would know it's just it's an elimination process, Gaussian elimination process to include certain variables as introduce them into basis and eliminating certain variables, excluding them from the basis. That's the basic idea. And then it associated with optimality test and feasible test to decide which variable should be entering and which variable should be leaving. That's the idea. And then at the end, you could test, you do the pivot, do the Gaussian elimination, and then at the end, you can test whether it's optimal. So continue, and then the solution is identical to the previous method as well. By the way, I think some of you actually even the same problem using different method come up with different conclusions. Then you should start questioning, maybe one of them is wrong. That's the way that you have done. So just a sanity check in some regard. And then this is some code to do it. Yeah, this is some linear algebra there. And then the last, two more. This one is for the sensitivity, and then seeing that what's the range that this particular C2 should okay, for this in this section, determine sensitivity optimal solution to the change of C2 using objective function of this. And then slope of the objective function can be -25 divided by C2 in this case, because 2D x1 and x2, and then the slope of constraint 1, which is one of them is this, the other one is that. So you can see that constraint 2 is there, constraint 1 is there, and then it has to be in that range so that you can get the variable to say that C2 has to be between 20 and 37.5 in this example. And then the last question is using curve fitting to minimize the sum of the absolute deviation of the following models and data set. And then you can see that using different tests, y could be ax, could be a squared x, etc. And then look at them, how this particular solution actually explained the possible solutions. And then that's everything that I want to cover for today. I don't really have anything planned. So do you have any questions? No? Okay, so if you don't have any questions, make sure that you would remember to form the team by end of next week. I'll start putting something on the Blackboard system in a couple of days. Okay, thank you, and have a good weekend. Have a good week.